Okay, so we have exam on Friday, and the exam will cover from the it'll basically be SN1, SN2, E1, E2. E1 and E2 are new. It will include the problems of if I give you two reactions and change something like if I change the solvent or if I change the nucleophile, does one reaction go faster or slower? Do they have the same rate? Those problems will be on there this time. E2 is not part of those problems. Okay, so there is no, if you've been looking for problems like faster, slower for E2, they're not there because that's not appropriate for E2. Then mechanisms of SN1, SN2, E1, E2, dehydrations, SN1 and SN2 and E1, E2 reactions of alcohols, like what the take-home problems, the take-home quiz was. And I will have those outside my door in the box this evening. The answer key is online, I just haven't fully graded them yet. Then for additions, electrophilic additions, you know, HCl, HBr, HBr peroxide, H plus H2O, all the reactions we talked about last week, the mercuration, demercuration, bromine, borohydride, hydroboration oxidation reactions. So basically everything up to this point will be on Friday's test. It'll be mechanisms, it will be writing products and determining major products, and it will be the faster, slower, same problems. And last time it may seem like it was multiple choice. It really wasn't. It's just R&S made them, it was easier for me to grade and a lot faster to use the Scantron forms for R&S and for the other problems. This time there won't be that, so there will still be choose reaction A or B, or they have the same rate, but there's not enough problems to put them on a Scantron, so it'll be all written out. And Wednesday we can use that period for questions if you have questions. Okay. So the website, as far as I know, should be up to date. There were some problems dealing with, is the reaction writing products, and then is it regio or stereoselective? That will also be part of the Friday test as well, regio and stereoselective. Any questions off the top of your head? The older tests from the last 2 years fit this timing, so that means they would be good practice exams. Older than the past 2 years will have lots of problems, but they may have some problems that were on the last test because it was a little bit slower pace. Okay, so where we left off on last week, whenever that was the idea of adding OHs to double bonds. So we could add an H and an OH, Markovnikov, and Markovnikov 50% cis, 50% trans. We could add the H and the OH anti-Markovnikov, with the H and the OH adding 100% cis, which was the case for hydroboration oxidation. And then the mercuration, demercuration adds H and OH trans, but Markovnikov as well. So then the next reaction, series of reactions that we want to talk about are triangular intermediates. And these are true, I guess these are true intermediate compounds, which are called epoxides. So epoxides have an oxygen attached to 2 carbons. There can be other things attached to these carbons as well. They don't necessarily have to be these carbons don't necessarily have to be CH2s. They can have other groups attached to them. And that's what will make them interesting, is the idea if I've got 2 methyl groups on one carbon and no methyl groups on another, then I can have a regioselectivity to them. But epoxides are truly intermediate compounds. You can buy epoxides, you can make them, you can put them in a bottle. They're stable. And they have the oxygen attached to both carbons. They're triangular intermediate compound, and so all the reactions that they undergo will be trans, just like all of our other triangular intermediates. So how do you make them? Well, first way to make them is using bromohydrins, because bromohydrins are pretty boring. It's okay to add Br and OH to a double bond, but one of the reasons we use bromohydrins is that when we add our Br and our OH, and remember that adds 100% trans, that when we then deprotonate the OH, so if we use hydroxide, hydroxide will come in and it will deprotonate the OH of the epoxide, or of the bromohydrin. That makes an O-. That O- then is perfectly set up to do a backside attack on that carbon and kick the bromine off, so it does an SN2 reaction. So in a cyclic system, if I make the bromohydrin, the Br and the OH are in a perfect position to form the epoxide. If they were acyclic, then I'd have to rotate around to put the bromine and the O- trans, but the reaction already sets them up that way. So one of the uses of bromohydrins is to make epoxides by this 2-step process. Okay, so that's one way. It's not the preferred way. The preferred way is to use a peroxy acid. And a peroxy acid is something that has an extra oxygen added into a carboxylic acid. So that's an R, C double bond O, O, OH. And that per term, that's what that refers to. If we talk about hydrogen peroxide, we could call water hydrogen oxide. With the extra oxygen, it becomes hydrogen peroxide. So whenever you see the term per, it means there's an extra oxygen in there. And so with these peroxy acids, one of the 2 oxygens ends up adding to the double bond. The MCPBA must have been from last week. That is a very specific type of peroxy acid that is used. It's called meta-chloroperbenzoic acid. So there's perbenzoic acid and there's metachloro. So that's the actual structure of MCPBA. You don't have to know that because I use the peroxide, but in the sapling problems, they'll probably talk about MCPBA. And that's what that is. It's peroxy acid. Okay. Oh, I used the circle. Probably shouldn't have used the circle. We'll get to the circle next semester. So there's MCPBA. We're not going to talk about the mechanism of this other than to say this. The oxygen gets added directly to both carbons at the same time. So if you think about MCPBA, it's like a Br+. It sits right on top of the double bonds, and both bonds are formed at the same time. And what that means is, that means that if I had, for instance, like the trans alkene, that over here, the 2 R groups would be trans. So whatever the stereochemistry of the alkene is, that stereochemistry gets preserved in the product. So if we've got a cis or a trans, in this case alkene, the epoxide becomes trans. And that's important in terms of the mechanism, because it means that the oxygen doesn't add to one carbon and then have the other one rotate around and then form the second bond. They both form at the same time. So it's like a bromonium ion. That gives us a new type of term. We've talked about stereoselective, we talked about regioselective. There is another term called stereospecific. And stereospecific means that if you change the stereochemistry of the reactant, you get a different product. Okay. You would think that stereospecific would mean something else. And this is not what it means. You think it might mean 100-0. But that's not stereospecific. Stereospecific, the term stereospecific means that if I use the trans alkene, I will get the trans epoxide. If I change the stereochemistry of the alkene to cis, I'm then going to get the cis epoxide. So stereospecificity means that if you change the stereochemistry of the reactant, you get a different product. It also can mean that some reactions will be no reactions if you change the stereochemistry of the reactant. And so a lot of times you'll hear when they talk about biochemistry or molecular biology in terms of chirality, most of biochemistry, well, a good portion of biochemistry is stereospecific. That means that one chiral reactant gives one product and another chiral reactant will give a different product. And sometimes it'll be in the case of sugars. If you have our sugar that we used in lab to do the fermentation was D-glucose, or it was sucrose. But D-glucose is what we end up metabolizing. If we change the chirality of the glucose and all of a sudden the glucose became all L, we die. Because there's no way we can metabolize the other form of glucose. And that's an example of the stereospecificity. You get one reaction with D, you get another reaction, no reaction with L. And there's a lot of biochemistry reactions that work that way. I think there's an essay question that some people give in their organic class, like Alice walks through the mirror, and all of a sudden she becomes her mirror image. What can she eat? And how long before she dies? Because of the bad biochemistry reactions. But what can she eat? I'm not going to ask you that question. But that's what stereospecificity means when it comes to biochemistry. We've talked about one other stereospecific reaction besides this oxidation. And that is, we've talked about SN2. R gives S. If I change R to S, what happens? I get a different product. So the other stereospecific reaction we've talked about is SN2. But those are the three terms: stereoselective, regioselective, and then stereospecific actually is in its own category of reaction. So the whole idea here is I'm making epoxide. I can do it in one step with MCPBA or peroxy acid. I can do it in 2 steps. How do I go backwards? I can do it 2 steps from bromohydrin. So the preferred method is MCPBA. That's the preferred method. So then the question becomes, if I make an epoxide, big deal, what can I do with it? Well, what we do is we open up epoxides. And we open up epoxides by adding acid. We can do this a couple of ways, but I think at this point I'm only going to talk about acid-catalyzed ring opening. So acid-catalyzed ring opening, if I take an epoxide and I add acid to it, and I was to not have the reaction here for you to see, and I said, what's the first step in the mechanism? Hopefully you would say, well, there's an oxygen, there's acid, protonate the oxygen, which is what you do to make an oxonium ion. Now, this oxonium ion is actually bonded to both of those carbons. Oxygen isn't real happy with the positive charge because it's electronegative. So what it can do is it can essentially make partial bonds to each of these two carbons, and then pass some of that electron density into the two carbons that are much more happy to get the positive charge than the oxygen is. Right? So that's, I'm having a sense of deja vu there. I got an atom bridged over two carbons with delta pluses. Where have we seen that before? Where have we seen this structure before? The bromonium ion? Yeah. So bromonium ions with the Br plus, it's over the double bond. Bromine's not happy with a plus charge, so it transfers its plus to the two carbons and it forms partial bonds. Where else have I seen that type of structure? I'd say you, but apparently you were still looking for it. So in addition to bromonium ions, where else do we get this triangular intermediate? With what? The mercury. So the bromine and the mercury also form these triangular intermediates, which is why they all kind of come together, and also why we'll talk about epoxides now, since the, well, I would say since the triangular intermediates are fresh in your mind, and they will be by Friday. Hopefully. Because now everybody's here to stay. So then water adds. Water adds from underneath. So that means that really that OH should be down here. So I'm going to end up adding two OHs, 100% trans. Now let's make things interesting. I'll add a methyl group here, a methyl group here, and two hydrogens there. And I'll call this carbon A and carbon B. So where does the water add in that triangular intermediate? We know it adds underneath because it's a triangular intermediate. That's what the triangle does. Where does the water add? Carbon A or carbon B? Or 50-50 to both.
Would be A has more hydrogens, the Markovnikov product?
A, sure, A doesn't have more hydrogens. In this molecule, if this is A and that's B, B has more hydrogens. You just don't want A?
Well, if we will get a Markovnikov product, then it would be B.
Okay. Let's take a step back from that for a minute.
Okay.
Emily?
I think both.
50-50?
Yeah.
Okay.
So you're adding the same thing, kind of. Like a OH.
Well, I'm adding water.
Yeah.
I'm adding water, but where's the water going to add? A or B? You say 50-50. Any other answers? Courtney?
I want to say B because I think that the methyls can have more electron clouds to disperse the partial positive on A.
Okay. So I got 50-50. I got a B. I got Markovnikov's rule somehow coming into play. Anybody want to go for A? I do. I want to go for A. Am I right? I hope so. So let's deal with a couple issues. First of all, Markovnikov and anti-Markovnikov only deal with adding electrophiles to double bonds. So when we do epoxide reactions, there's no Markovnikov, anti-Markovnikov. All right, and that happens when you learn those terms. You start using them for different things. Markovnikov and anti-Markovnikov only refer to double bonds and additions to double bonds. They have no other use. And they have absolutely no other use. They're not appropriate in any other reaction. Right? It's like, I guess the only thing that comes to mind would be a sports analogy about talking about football players in the dugout. It's not an appropriate term. So Markovnikov doesn't work with this reaction. It only works with double bonds. There's similarities that sort of look like it, but it's not Markovnikov. Secondly, the issue of which carbon has the greatest delta positive charge is what we're looking for. So I have a weak nucleophile. My weak nucleophile is forced to add to the carbon that has the greatest delta positive charge. That's the guiding principle. And it's got to add underneath because it's a triangular intermediate. So the question really is, which of the two carbons, A or B, has the greatest delta positive charge? Somebody give me an answer. Which carbon has the greatest delta positive charge? A or B? A. Because A is the most substituted. If I'm looking at those two carbons, I would sort of look at A as if it was kind of a tertiary carbocation, because it's got 3 carbons attached to it. I would kind of look at B as if it was a quote-unquote primary carbocation. So the alkyl groups stabilize the positive charge. That's kind of counterintuitive, but the more alkyl groups, the greater the positive charge, because it's able to stabilize that. Sometimes people will say B because of sterics. They'll say, well, B's least sterically hindered. So it'll add to B in sterics. Well, that would be true if this was a strong nucleophile, and we'll come back to that. But when I'm adding a weak nucleophile, the reaction really goes SN1. As far as it choosing the carbocation or choosing the carbon with the delta positive charge to add to. Now, it does attack from the backside, so it has this SN2 characteristic. But that's only because there's no lobe here. Remember, we get a 50-50 lobe, or 50-50 addition to the lobes, but there really isn't a top lobe to add to, so it has to add to the underneath lobe. So it will add to carbon A. In this case, almost 100%. Anybody remember that from last week? Because if I go back to last week, that's exactly what I wrote last Monday. Where's the water going to add in the bromonium ion? It's carbon A. Why? Because it has the greatest delta positive charge. Because this looks like a primary, this looks like a tertiary. That's okay. There's been 7 days in between then and now. And I've decoupled. You're remembering things from my teaching. I did that about my second year. Go forward. Okay. Everybody understand that? Normally they come right after each other. Why? Because it's the same thing.
So is that determined that the most substituted carbon will take precedence over being sterically hindered? Or there are exceptions to that rule?
If it's SN1, it's got to go to the carbon most substituted. It's not even a question of steric hindrance, because what we have is we have a different mechanism. SN1, what governs SN1 reactions? Tertiary carbocations react faster than secondary, react faster than primary. We know that the water being a neutral nucleophile has to do SN1. So in this context, it means that carbon with the most delta positive charge is the one it's got to add to. Sterics doesn't have anything to do with it.
Does it ever come into play?
If it's SN2. So if I took this water and made it a hydroxide, it would add to carbon B. But we're going to deal with acidic opening first, and then we'll go back to basic opening, basic ring opening. So yeah, it will become SN2 when it's a negatively charged nucleophile. So I added H and OH, or OH and OH, 100% trans, but who cares? Because I added 2 OHs, so how do I know where they came from anyway? Right? In the overall scheme of things, I've added 2 OHs. Whether they had 100% trans, that's important. But whether the water added to carbon A or carbon B doesn't matter, because I got 2 OHs. But you know I can take care of that and make it important for the epoxide. All I got to do is add something new to the epoxide, which I will. Everybody kind of okay with this? So when this comes one after another, not with a week in between, we talk about bromonium ion, we say, hey, that epoxide, a protonated epoxide looks an awful lot like a bromonium ion. So we can save a little space in our heads for trivial stuff if we just combine those two and say, oh, they look the same, they react the same. All right, well, I guess in this case, I would take my epoxide. Let's put a methyl group here to make things interesting. Let's add H plus and methanol. Because if water's going to add another OH and I'm not going to be able to tell the difference between the two OHs, change the OH from HOH to ROH and you get the same reaction. So if I did this reaction, can you write the major product of the reaction? Showing the stereochemistry. Let's see, are regioselectivity and stereoselectivity still appropriate here? They could be. Although we don't normally use them, they could be. So if I'm writing the 4 possible products of this reaction, I'd write 4 of these. If I was going to have a multiple choice question, this would be my multiple choice question. I'd probably, now that I have up to 10 choices, I'd throw a few more in. I might have a couple of OHs in there just to throw you off, and who knows what else I'd have. So if I was to ask what's the major product of the reaction, A, B, bless you, A, B, C, or D? And then I could have A and B, A and C. If I was really in the mood to have low scores, I would have you bubble in any and all correct answers. So that way you only get full credit if you get all of them exactly correct, because I don't know how the computer does. The computer doesn't do partial credit for those. I'd have to do those by hand. That defeats the purpose of the Scantron. So what would be our major product of the reaction? How many people say A? B? C? D? More than one. All right, so the most popular answer was C, which is correct. So what's going to happen in this mechanism? If I asked you to write out this mechanism, I would end up with the protonation on the OH, or the protonation on the epoxide. That's going to give me a positive charge on the oxygen, which is going to be distributed basically amongst those 2 carbons. Where does the alcohol now add? To the top carbon or the bottom carbon? Well, C is the correct answer. It's got to add to the top carbon. So the alcohol will add to the top carbon, then the OH will end up on the bottom carbon. So in this case, it doesn't matter how you draw it, but the OH and the OCH3 have to be trans. So you end up with the OCH3 attached to the carbon with the methyl, the OH attached to the other one, because as the methanol comes in and adds, the OH goes to the other carbon. And then I end up with them adding trans. So this, oh, good question. So those two products that I have circled, those two molecules, what's their relationship? Ooh, very good question. Because it appears as though I wrote a different product when I wrote the mechanism out than what I wrote originally. Did I? So what's the relationship between the two circled molecules? Enantiomers? Diastereomers? Same? Meso? What are they?
Enantiomers.
They're enantiomers. How do I know that? Because I should at this point in the semester. Top carbon has what configuration? I switched the groups, so it's opposite, bottom has opposite as well. So two opposites, enantiomers. So either, actually those two products are formed what, 50-50? Okay. So when we open up epoxides using acid, the OH will end up on the carbon that's least substituted, and the nucleophile will end up on the carbon that is most substituted. Right. The OH will end up on the carbon that's least substituted. The nucleophile, in this case methanol, will end up on the carbon that's most substituted. Now, that description of the products kind of makes you think that it's Markovnikov addition. So that's where you can get Markovnikov thrown in here, but it's not an appropriate term. So that's how we can add those reagents. So I'm going to add trans. What else could I add? So if I can add H plus and H2O, my next substitution is H plus instead of H plus HOH, which is water, H plus HOR. That's an easy substitution. What else could I do with an epoxide? Well, at the moment I could add, how about H plus and Br minus? How about H plus and Cl minus? Those are interesting. Because if I add H and Br to an epoxide, the net result is that I've added OH, or I get an OH on one side and a Br on the other. That's sort of like a bromohydrin. Kind of. Except the regioselectivity is different. In one case you get one orientation, the other one you get your other orientation. But you know what? We'll talk about that a little later. What else do I have with epoxides? Nothing. So right now we're just going to deal with acidic epoxide ring opening. Basic we'll do later. All right, everybody still kind of with me? All right, so those are electrophilic reactions of two alkenes, but that's not where we're done. We can also do other things with alkenes. We can add things, but they're not going to be electrophilic. They're not going to be an electrophile plus a nucleophile. So what else can I do? I can reduce them. I can do hydrogenation. In lab, we talked about the idea that reduction in organic chemistry means you add hydrogen, you lose oxygen. Oxidation is adding oxygen or losing hydrogen. It still involves loss or gain of electrons, but those are hard to see. So when we talk about oxidation and reduction in organic chemistry, we usually talk about gaining hydrogens, losing hydrogens, gaining oxygens, losing hydrogens, or oxygens. So in this case, I can reduce a double bond by adding hydrogens to it using hydrogenation. And so hydrogenation involves adding hydrogen and either palladium or platinum metal. That adds the two hydrogens, cis, and Markovnikov and Markovnikov are irrelevant because symmetrical reagent. I'm adding two hydrogens. Doesn't matter whether I add them this way or this way. Still adding two hydrogens. Hydrogenation. That term shows up in non-science, right? Because we can have the partially hydrogenated fats, I think. Those are evil, right? The partially hydrogenated ones. That's what they do. They take double bonds in oils and reduce them to alkanes, and liquid oils become solid fats. And they're apparently bad for your health. We'll talk more about that later. So here's the mechanism, the quote-unquote mechanism, you may want to say, oh, how do I remember that those two are cis? Well, you can just remember that. Or you can remember this picture. What happens is hydrogen is on the surface of the palladium or platinum metal. The alkene then approaches and the two hydrogens add to the same side, all in one step. So hydrogenation gives you the cis addition of alkenes, or cis addition of hydrogens. Turns an alkene into an alkane. Ooh, carbene additions. Maybe we need to come back to carbene additions. I don't feel in the mood to do carbene additions. We'll come back to those. Since we're adding stuff cis, let's just continue to add stuff cis. So H2 and palladium, or H2 and platinum, adds two hydrogens cis. You want to add two OHs cis. Well, I actually know with an epoxide that I can end up with the two OHs trans. So now sort of the yang of that, if we're talking about the yin and the yang of synthesis, being able to do one thing one way and then doing it the opposite, if I can basically get two OHs next to each other trans, can I get them cis? Yes. A couple of ways. Cis hydroxylation. So hydroxylation means add two OHs to a double bond. Two reagents I can use. One is called osmium tetroxide and peroxide. The other one is KMNO4 and KMNO4 and base. Now KMNO4 and base is going to turn into KMNO4 and acid and do something totally different here. But those two add two OHs cis. Can the reaction be regioselective? It says it can't. Why can't it be regioselective? Because I'm adding two OHs symmetrical reagent. Can't be regioselective. Can it be stereoselective? Could be, because the OHs are adding cis. 100% cis. How does this reaction work? Well, if I add the KMNO4 and base to a cyclohexene, I definitely get cis diol over trans diol. And that's how I can tell that the reaction is actually stereoselective. the reagent the reason that this works, and again, this is not a mechanism you have to memorize, but here's what happens. What happens is that the arrows move from the double bond to the oxygen, from the double bond into manganese, from the double bond oxygen over here to the carbon, those green arrows, off the permanganate ion. In essence, the permanganate, well, not in essence, the manganese atom gets 2 electrons. So it gains 2 electrons. So let's see. If the manganese gains 2 electrons, that's GER of the Leo. The lion goes GER. GER is gains electron reduction. So manganese undergoes reduction. That must mean the other molecule undergoes oxidation. And it does, because it gains oxygen. So then we make that 5-membered ring permanganate compound. It's in the upper right-hand corner. So sometime last week, I'd say, remember last week when I talked about that, but we're not doing so well on that. We talked about 3-membered rings cause things to add opposite. When you add 2 things through a 4-membered ring, how did they add? Same side or cis. Because the 4-membered ring wasn't big enough to stretch across the double bond to add one thing to the top and one thing to the bottom. Same thing's true for a 5-membered ring. It's not big enough to add the oxygen to one side of the ring, then stretch all the way around and add the oxygen to the bottom side of the ring. So this is a 1-step process right here, and that will end up adding both oxygens at the same time. But since it's only a 5-membered ring that's going to form, those 2 oxygens have to add cis. Then when you add peroxide, the peroxide ends up stripping off all the manganese stuff, and we're left with the 2 OHs cis. Okay. So again, a 5-membered ring, when you end up with a 5-membered ring product or a 5-membered ring transition state, the best it can do is add cis. It can't add trans. Same thing was true for a 4-membered ring. So then I end up with my 2 OHs cis to each other. So that's cis hydroxylation. Osmium does the same thing. Osmium tetroxide, there's plenty of KMNO4 around. I mean, KMNO4 is a purple solution used in general chemistry for titrations. Sometimes you add it to an aquarium to oxidize all the organic crap and make the fish tank clear up. Doesn't kill the fish, it just oxidizes all the organic stuff up. Makes it water soluble, basically. The KMNO4, you can add 1 mole to 1 mole, but osmium is so expensive that with the osmium tetroxide, what we end up having to do is to add a small amount of osmium and then a lot of peroxide, so that after the osmium adds to the double bond and the peroxide takes it away, then the osmium gets regenerated into its reagent. So it's catalytic, basically, because it's too expensive. KMNO4 is cheap. So there's the mechanism for the osmium tetroxide. Same thing. Then the second step, the peroxide reacts with it and it makes the osmium, it regenerates osmium. Okay. All right, so those are additional reactions of alkenes. I think we'll stop the test, though, at what we had covered up to this point before today. So all the hydroboration oxidation would be the last one. So Wednesday, questions. If you have questions before that, feel free to ask. I will have the take-home quizzes from last week outside the door. Other stuff is already out there, so feel free to pick that up.